In this class, we'll get to know about machines. What is a machine? You must have heard about it earlier in your earlier classes that what is a machine, and you would state that a machine is a device that makes our work simpler. But now we are in a position that we can get to know that how does a machine makes our work simpler. But before moving to that part, we must know about these simple terms, these basic terms, that is effort and load. What is effort and what is load? As the term sounds, load. What is load? Anything, any weight or any object that we have to uplift or we have to cut, that is, we have to overcome that force, that is known as load. Any resistive force or any, we can say that any opposing force that we have to overcome is a load. It might be anything, that you have to cut a paper, you have to cut a cloth, or you have to uplift a heavy load. All of these things will be the load. So basically what is load? It is the resistive or opposing force, resistive or opposing force that has to be overcome, using the machine. So this term overcome, we have used this term here. Why? For what? If you are cutting a paper, if you are cutting a cloth, if you are raising a heavy load, all these terms, they are included over here. So we use the term overcome. Overcoming what? Overcoming the resistive force. So what is load? It is the resistive force or opposing force that has to be overcome using any machine. Obviously, as it is a force, so the SI unit for it must be Newton. You know about the SI unit for force. Now, what is effort? As the term sounds, effort, it means that it is the force applied by us. On what? On the machine, because we are using the machine to do our work, to make it simpler, to make our work simpler. So what is effort? It is the force applied or exerted by us. On what? Obviously on the machine, because we are using to do our work in a simpler way. So what is effort? It is the force that is applied by us on any machine to do our work, to make our work simpler. So now we know about both the terms load and effort. Now we can move to our topic, that is about machines. Now we will be talking about that how does a machine makes our work simpler. So a machine can make our work simpler in either of the following four ways. Such as, if we have a scissor, we can use the scissor to cut a cloth or to cut a paper. If we have a nutcracker, then we can use it to crack the nut, to break the nut easily by applying a lesser effort, by applying a smaller force. The machine can make our work simpler in the following four ways. Any of the simple machines, they can make our work simpler in either of the following four ways that we are about to discuss. The first way in which a machine can make our work simpler is it can act as a force multiplier. Firstly, we will be talking about the force multiplier, then we will move to the speed multiplier. The machine, it can act as a force multiplier. Now, as the term sounds, whenever we use the term multiplier, what do we mean? We mean that there must be an increase. The force must be increased. So, it can act as a force multiplier. We will have some examples over it. for these force multipliers, suppose that I told you earlier about the nutcracker. What does it do? The nutcracker, we use it to crack, to break the nut easily. We apply to do so. In order to do so, we apply smaller effort on the machine, on the nutcracker, and it enhances the force. It increases the force, that is the effort applied by us on the machine, on the nutcracker, and hence our work is simpler now. It makes our work simpler. Now the second, we will have the example for it, that is the nutcracker. Or there are many examples for it, such as the crowbar. Crowbar, it is nothing but it is a rigid, straight or bent bar. It might be straight or it might be bent, and that is capable of the bar. It should be capable of the crowbar. It should be capable of turning about a fixed axis, that is its axis of rotation. So we move to the second case, that is about the speed multiplier. The machine can also act as a speed multiplier. It can act as a speed multiplier. Again the same part. Multiplier means there must be increase in speed. There must be enhancement in the speed. There must be a gain in speed. Gain in speed of what? Suppose we have example over here. We have the example of scissor. This part. It is what? It is the handle from where we apply the effort, from where we apply the force. And this part, this is the blades. This is the blade. That cuts the load. It might be the cloth or it might be the paper. So this is the blade and this is the handle. What do we do to use the scissor, to operate the scissor? You apply the force, you apply the effort. Suppose we apply the effort from this point. So it is the effort point. It is the point of application of effort. It is our effort point. And the load, the cloth or the paper that has to be cut, we place that part, that thing in between these blades. Suppose this is our load point. Obviously, when you use the scissor, what do? The handles, they also move in this direction, and these blades, they also move like this in this direction. As you can see, it's very clear from the figure that the effort, the point of application of effort, when you use the scissor, the point of application of effort, it would move from this position to this position. They will come closer to each other. So we can denote it with DE. That is the displacement of, this is the displacement of point of application of effort. And what about this part? Obviously, these blades will also come closer to each other. You know about the scissor, how does it work? So these ends will also come closer to each other. So if it is the load point, the load is also being displaced. The load point is also being displaced. It is denoted by DL. In most of the cases, people get confused between these two parts. I'll tell it about it to you later. But now I am only giving you a hint that this DL and this LA, that is the load arm, these are two different things. What do we conclude here? DE, obviously, DL, it must be greater than D. You can see here from the figure. DL, that is the displacement of load, it is greater than the displacement of effort. And obviously both the phenomena, both these things are taking place simultaneously. It means that the time taken for both these phenomena is similar, is the same. So if you divide it by T, as the time for both these both these phenomena is the same. So you know that displacement by time, what is it? It is velocity. So it will be VL, velocity of load, and it is VE, that is the velocity of effort, point of application of effort. What do we conclude here? The load here, it moves at a faster rate than the effort. So what does this simple machine do for us? It acts as a speed multiplier, because for a smaller movement of effort, there is a larger movement, there is a larger displacement of load. And so we conclude that this scissor, it acts as a speed multiplier. The third case, the third way in which a machine can make our work simpler is by changing the point of application of effort. By changing the point of application of effort to a convenient point. Now we will have a simple example for it. You ride a bicycle. You ride a bicycle. What do? We exert a force at the pedal. If suppose that there is no pedal attached to the wheel, the toothed wheel, with the help of which the chain rotates, and along with the chain the rear wheel rotates. From there torque is produced. You know about torque now. So if suppose this is the toothed wheel, over which the chain runs. Now suppose that if we are not provided with the pedal, then where do we apply the force to rotate this tooth wheel to produce the torque? We can apply the force over here or here, anything, at any position, But if we attach a pedal over here, then our work, it becomes simpler. Now we can exert the force with the help of our legs at the pedal, and this makes our work simpler. So what do we do here? We exert the force, we apply the force, the effort at a more convenient point. So this pedal, the pedal is also a simple machine, and what does it do for us? It changes the point of application of effort to what? To a convenient point. So this is our convenient point. The pedal is the convenient point where we can apply the force, we can apply the effort very easily, and our work is done in a simpler way, is performed in a simpler manner. Now, what about the fourth part? What about the fourth way in which a machine can make our work simpler? The fourth and the last way is by changing the direction of effort to a convenient direction. I'll give you a simple example for it. You are provided a task that you have to draw a bucket that is filled with water out of a well. What do? We exert a force in upward direction so that the bucket is also pulled out of the well. In that case, you are exerting the force that is opposite to the force of gravity. Suppose that this is the bucket and you have to pull out the bucket that is filled with water. Now, if it is attached to a rope, attached to a string, then you have to apply the force in upward direction, and obviously there is a force acting on it that is in downward direction. That is the weight of the bucket along the water itself. Now, in this case, you are exerting the force in the direction opposite to the force due to gravity. obviously that would be difficult for us. That would be not that much easier for us. But if we use a pulley over here, suppose that this string, it passes over a pulley. Here we have a pulley over which the string passes. Now this string comes at this end, and the person, suppose I am provided with the task that I have to pull this bucket that is filled with water out of the well. Now in this case I do not have to apply the force in upward direction. This time I'll apply the force in downward direction, in this direction, and now I am not exerting the force in the direction opposite to the force due to gravity. Now I am applying the force in the direction of force due to gravity. One more part. In this case, I can act my own body weight. I can apply my own body weight as the effort. I can hang myself on this string, on this rope, and apply my whole body weight as the effort. So this makes my work simpler. So this is the fourth case, the fourth way in which a machine can make our work simpler, that it can change the direction of effort to a convenient direction. Obviously, when there was no pulley, the force was exerted in upward direction, and that direction was not convenient for us, was not simple for us. But when we use this simple machine, this pulley, then now we have to apply the force in the direction of force due to gravity, and that direction is convenient for us. So these were the four ways in which a machine can make our work simpler. Now we move to the next part. Now we will get to know about the mechanical advantage and the velocity ratio of a machine, of a simple machine. Mechanical advantage. It is abbreviated as capital M dot capital A. It is defined as, wherever you hear this term advantage, what comes to your mind? That there must be some benefit, there must be some profit. So if we are using any machine, then what is the benefit behind it? What is the advantage behind it? And mathematically, we will get to know about it. What is mechanical advantage? It is defined as the ratio of the load, that is capital L, to the effort, that is capital E. If you are asked to define it, keep it in mind. Firstly, you will give the theoretical part, you will define it, and afterwards, you will give the mathematical expression for it, that is L by E. What is mechanical advantage? It is defined as the ratio of what? The ratio of load to the effort. Now, we will have some cases over here. If the load is greater and you apply a smaller force on it, on the machine, to overcome the load, as I told you earlier about the nutcracker, you apply a smaller force on the nutcracker, and the nutcracker, it enhances, it increases, it multiplies your effort. As a result, you can overcome a larger resistive force, you can overcome a larger load by applying a smaller effort, by applying a smaller force. So in this case, if we are talking about a force multiplier, it can be asked to you that the load is greater and the effort being applied is smaller. Then what kind of machine is it? If L is greater than E, it means that the load is greater and we can overcome the larger load, the greater load, by applying a smaller effort, by applying a lesser effort. So in this case, as you can see here, what will be the MA? L by E. It is L by E. In this part, L, that is the numerator, it is greater, and the denominator is smaller. It means that L by E, that is MA, is greater than 1. Because I'll mention the reason here. L by E here will be greater than 1 because the numerator is greater and denominator is smaller. So what do we conclude? The MA is greater than 1. And let me tell you that whenever MA is greater than 1, it means that load is greater than effort. You are overcoming larger load by applying lesser, by applying smaller effort. So this type of machine is known as a force multiplier. It might be possible that you are provided with these cases, with this information, and you are being asked that what kind of machine is it? So it is a force multiplier. Whenever the MA of any machine is greater than 1, the machine must be a force multiplier. Now we move to the second case. It was the case 1. Now we move to the second case. Case 2. L is less than E. It means that now the load is greater, is less, and the effort is greater. In this case, what is MA? It is L by E. Since L by E, it will be less than 1, because as you can see, the denominator is greater and the numerator is smaller. So L by E is less than 1. So here MA is less than 1. I'll tell to you about it that MA, with this reference, with this relation, we cannot state confidently that this machine must be a speed multiplier. But when we discuss about the term, the physical quantity, that is velocity ratio, about the ratio, that is velocity ratio, then it would be more clear that in that case we will tell that the machine is a speed multiplier. So these type of machines will be known as the speed multiplier. If the MA is less than 1, compare them. MA greater than 1, force multiplier. MA less than 1, speed multiplier. Now we move to the case 3. Case 3. In this case, L is equals to E. And the simplest example that we have discussed now only, that is the pulley. If you are asked to draw the bucket that is filled with water out of the well, then you have to apply the force, and the force have the magnitude of force, it must be at least equals to the weight of the body, weight of the bucket itself. So there is no enhancement in force, the force is not being increased, the effort is not being increased, or the speed also is not being increased. There is no gain in speed. It only changes the direction of effort. From now, by using the pulley, we can exert the effort, we can apply the effort in downward direction. That is convenient for us. So in that case, there is no gain in speed, there is no gain in force. L is equals to E. Now what will be the MA over here? Obviously it will be equals to 1. So these type of machines, if you are provided with the information that a machine has MA equals to 1, what kind of machine is it? So this kind of machine, it can be used to change the direction of effort. It can be used to change the direction of effort. In which direction? To a convenient direction. So this was all about the mechanical advantage. In the next part, we'll get to know about the velocity ratio. Now we will discuss about velocity ratio. This term, it is abbreviated as capital V dot capital R. As the term sounds, velocity ratio, it means that it must be the ratio that will compare the velocities. Velocities of what? Obviously here we have two things only, two forces only, that is the effort and the load. So it must be telling us about the ratio of the velocity of effort to the velocity of load. What is it? If you are asked to define it, that what is velocity ratio? It is defined as the ratio of velocity of effort, that is denoted by VE, to the velocity of load, that is generally denoted by VL. So this is the velocity ratio, and mathematical expression for it will be VE by VL. What is velocity ratio? It is the ratio of velocity of effort to the velocity of load. You know the meaning of this part, that is VE, velocity of effort. It means that the point of application of effort, it is moving at a certain rate, that is the VE. It is the rate at which the point of application of effort is moving, is being displaced. As I told you, with the help of this example, with the help of the example of scissor, this was our DE, that was the displacement of point of application of effort, and this part, it was our point of application of load, and that is why this part DL, it was the displacement of point of application of load. This is the displacement. If the point of application of load, it comes from this position to this position closer to this blade, then this is the displacement of point of application of load. So as I told you, both the phenomenons, both these things, they are taking place simultaneously. So the time for each of them will be the same. We suppose that the time taken for both these processes is small t. What can we write? VE, velocity, it is displacement by time. So we can write it over here that VE is dE by t, and VL, it is dL by t. Very simple it is. T and T, they got cancelled. As a result, we get the ratio as dE by dL. So VR, it can also be defined as this ratio. VR, it can be defined as the ratio of velocity of effort to the velocity of load, or it can also be defined as the ratio of displacement of effort to the displacement of load. As you can see, this is a pure ratio. This is the ratio between velocities. So it has no units. Now, we will discuss some cases for it. Case 1. As I told you in the last topic, that was about mechanical advantage. If the displacement of effort, when we were discussing about the 4 ways in which a machine can make our work simpler, I gave you the example of a scissor, and in that, what did we conclude? That the displacement of load, it was greater than the displacement of effort, or we can also state that VL is greater than VE. We have done this earlier. That is, the load moves at a faster rate. The load moves faster than the effort. The load moves at a faster rate than the effort does, than the point of application of effort does. So VL is greater than VE, and I told you that such a machine, it is known as a speed multiplier. What do we conclude? If VL is greater than VE, or we can say that DL is greater than DE, the machine is a speed multiplier. So in this case, if you find the velocity ratio for such a machine, what will be the ratio? VE by VL. As I told you earlier, if a machine is a speed multiplier, the load will move at a faster rate. The velocity of load will be greater than the velocity of effort. So the VL here is greater than VE. It means that the denominator is greater than the numerator. VE by VL, it will be less than 1 because the denominator is greater than the numerator. What do we conclude here? As VE by VL is less than 1, and VR, we know about VR. VR is the ratio of VE and VL. So the VR, the velocity ratio, it is less than 1. So if you are asked directly, that you are provided with the information that a machine has velocity ratio less than 1, what type of machine is it? So you will directly state that the machine is a speed multiplier. So such a machine in which the VR is less than 1, it will be known as a speed multiplier, such as the scissor. Now we move towards the next case. It is just the reverse of case 1. VL was greater than VE. Now in case 2, we assume that VE is greater than VL. V is greater than VL means the effort, in this case the effort is moving at a faster rate than the load. It means that the displacement of effort, we can also write it as DE is greater than DL. It means that the displacement of effort for the same time interval is greater than the displacement of load. Or in the terms of velocity, we can state that the effort is moving at a faster rate than the load. So obviously it won't be a speed multiplier. Such a machine will be known as a force multiplier. We will find the velocity ratio for it also. It is equals to VE by VL. As you can see here, VE is greater than VL. What do we conclude? The numerator is greater than the denominator. So VE by VL is greater than 1, and so VR, that is the velocity ratio, it is greater than 1. The velocity ratio will be greater than 1. Now we move, and this type of machine, it will be known as a force multiplier. As I told you earlier, when we were discussing about the mechanical advantage, then in the case 1 we discussed that the load was greater than the effort, and thus the mechanical advantage was greater than 1. So from there we can easily conclude that the load is greater and the effort is less. By applying less effort, we can overcome larger load. So obviously the machine is a force multiplier. But according to the same condition, if the MA is less than 1, then we were not that much confident that if MA is less than 1, then the machine is a speed multiplier. But now, if the VR is less than 1, we can easily tell that if the VR is less than 1, it means that VL, the velocity of load, is greater than velocity of effort. So the machine must be a speed multiplier. Now, the case 3, when VE is equals to VL, or we can say that DE is equals to DL, as in the case of a single fixed pulley. In the next part, when I tell you about the pulleys, then we will discuss about it briefly. DE is equals to DL. It means that there is no gain in speed. The effort and the load, both of them are moving at the same rate. Neither the effort nor the load is moving faster. So in this case, VE by VL, what will be the VR? As both of them are equal, VR will be equals to 1. And as I told you in the last case, in the case of mechanical advantage, when the mechanical advantage was equals to 1, the machine was only used to change the direction of effort. Similarly, in this case also, when you are told that the VR is equals to 1, in this case also, the machine, it neither gives us the gain in speed, or it nor multiplies the force. It only changes. This is our case 3. Such a machine only changes direction of effort. And you know in which direction? To a convenient direction. To a convenient direction. So these were the 3 cases for a velocity ratio. What do we conclude? If the MA and the VR is greater than 1, then the machine is a force multiplier. Be very careful, very much careful. We are summarizing it. If MA is greater than 1, or if VR is greater than 1, the machine will be a force multiplier. Either of them. If you are provided with the information that MA is greater than 1, the machine is a force multiplier. Or if you are told that the VR is greater than 1, then also the machine is a force multiplier. If you are told that the VR is less than 1, then the machine is a speed multiplier. Or if you are told that the MA is less than 1, then also the machine will be a speed multiplier. And the last and the third case, if the VR is equals to 1 or the MA is equals to 1, in both the cases you say that the machine is used to change the direction of effort. In which direction? Into a convenient direction. So that was all about MA and VR. In the next part, we will discuss about the work input and the work output.